All right, in this pre-lab, we're going to talk about a strategy to help understand how to identify an unknown, but also what reagents of a certain family might be stronger than another. We'll be dealing with alkaline earths. As you can see, they're the group 2 metal cations, magnesium, calcium, strontium, and barium in particular. And we'll be dealing with the halogens, more or less in particular the chlorine, bromine, and iodine. Fluorine and acetine are part of it, but we're not going to be dealing with those today. One thing you should keep in mind is non-metal ions are colorless. So that would be, let's see if we can find some here. All of these guys, if they were to form ions like chloride, okay, or bromide, they would be colorless. All of these cations, when they form Ca plus 2, okay, that is colorless. There's a bunch of other anions: nitride, oxide, hydroxide, sulfate, carbonate, nitrate, and ammonium. These are all colorless. Ions in general are colorless. How can you tell if some are colored? What's going on? There's some that are colored, but they have transition metal ions in them. Transition metal, both words are critical. Transition metal, those in the middle of the periodic table. See, this one has chromium, that one's colored. This one is colored as well. But typically, if you just have an ion in the solution, now it's usually anions and cations are partnered up, so they are going to be colorless. Okay, colorless means clear. I mean, you won't see any color. It will look like pure water. Also be noted that you cannot find an ion alone on the shelves. If I wanted to go measure out some chloride, I can't find a pile of chloride ions lying around in a bottle. So I have to find them partnered up with somebody. I usually try to find them with something that won't react in the reaction. That is often sodium or potassium. Sometimes it would be calcium. But calcium, as we're going to find, has some interesting precipitation reactions. Okay, so ions do not travel alone. So when you look for a bottle in the lab and you're looking for some chloride ions, okay, what will they come with? You're going to probably find sodium chloride. But we say that this is a source of chlorides, or the chloride ion. Okay? It's also a source of sodium ion, but it may not be particular. It almost looks like a salt shaker. But I mean a bottle in the lab. That said, let us consider the part of the advanced study assignment where you have to decide about some relative strengths of some elements. Let's call them D, E, and F. This would be similar to like chlorine, bromine, and iodine. But they're not. Okay, totally something else, but it's similar to that. We want to know what happens when they come into contact or in solutions with their resulting ions. This would be like a chloride ion, the bromide ion, and the iodide ion. Okay? So when there is just D in the solution, in my particular example, the solution would be blue. If there was E in the solution, it would be orange, or this peachy color, calling it orange. And if there was just F, it would be red. If there was D minus in the solution, E minus or F minus, they are colorless. They will not change the solution. So for example, if you have a solution of E that's colorless, okay, and here this is supposed to be colorless, add it a little bit just so you can see that there's something there. A little bit of light blue, so it looks like water. But if we drip in now some D, okay, then we can consider that this is the reaction that's going on. D plus E minus. In this, you can see that D, this blue color, is no longer there. Blue is gone. So that means this is gone. Well, there's probably some colorless things. You can't really tell much, but you can tell the blue is gone. So that means blue must have turned into orange. What happened was an electron from E transferred over to D. And so if it loses a -1 charge, it goes to 0. and then D, gaining that one electron, becomes D minus. Okay? And we just said D minus, the colorless, is colorless ion. But since E was formed, we now have an orange in the solution. So if this reaction goes, and we're going to say it does, then we say that this reaction does take place. Reaction goes. See, we focus on what is here and how it turns here. Students often have their focus here, and they see, oh, look, a reaction went because it went from colorless. That's not what we're saying. Don't look here. Your eyeballs should be here, what's happening with D, and then what's happening in the final solution. We also say now, because this reaction did take place, that D is stronger than E as an oxidizer. But I do not mean E minus. I actually do mean D is stronger than E. Well, what does that mean? Well, consider the reverse reaction. I think I have that in the next slide. So the opposite reaction is, what if you had D minus in a solution? If you added E to it, which we said was orange, okay, since, well, if you add that now, and the reaction does take place, well, actually, in this situation, the reaction solutions are mixed, so these two are mixed together, and we see orange. Notice that there is no color change going from E, and E is still there. No color change in E. So the reverse reaction of the D minus plus the E orange does not take place because there was no formation of blue color, which would mean that that reaction took place. E is powerless to take an electron from D, so it doesn't take place. So we say from this, D is stronger as an oxidizer than E. All right, let's consider what happens if you had E and F together. All right, so we're going to take the fluoride, not fluoride, F minus, sorry, just F, and you're going to add in E to it. Notice E is this orange color, F minus, this ion is colorless. This is not fluoride, this is just DEF, okay? Random, arbitrary somethings, okay? So when we have the colorless ion plus the orange being added to it, we would expect when these two are mixed together that you would have orange. Okay, but what happens? We actually, in the test tube, as you can see here, we now have the indication that F has formed because an electron transferred from fluoride to, from F minus to E, sorry. And the E minus has formed. So this is what's there. These are no longer there, so we say a reaction does take place because the orange color is gone. So if your eyeballs focus on the E here, and you can see that it turns to red, so there is a color change that took place. So we can say in this reaction, E is stronger than F, because if F was stronger, this reaction wouldn't go. It would always want to be taking an electron from E and going back this way. So in summary, if between these three, we can say D is stronger than E, which is stronger than F. But if D is stronger than E and E is stronger than F, then D is definitely stronger than F as well. Okay? So there is our summary for my particular reaction that has nothing perhaps to do with your ASA or the lab, but the thinking and the logic is exactly the same. Let's consider that you have an unknown. And it could be sodium D or sodium E or sodium F, okay? In which the sodium really is, in this case, a sodium ion, the cation. Let's pretend in your unknown you have NaD. What did you figure out if it was D? Well, we could add the original D solution to it. Notice, not D minus, we got to keep that sorted. In the test tube where you have your unknown, okay, that's where your unknown is, it's colorless. But you add in the blue D reactant, and you see if something happens. And you notice there's a blue color. If you focus from here to here, you'd say there's a reaction that takes place, but that is the wrong place to be looking. You need to be looking from here, T, to here. Because if you were to add in there, it would be blue, and it is blue. So we say really nothing happened here, and you really wouldn't expect, because if it did, I mean, it's just forming the same thing. So you really can't tell. So we're going to say that this is no reaction. Or if it is, it's not an interesting reaction. It's not doing anything for us. Okay, let's say now you took another test tube that has your unknown in it, and you can add in E now to it. So you add in E, which is pink, or this peach, or orangish color. If a reaction would take place, we would say then E would then transfer an electron, or take an electron from D, and it should become E minus, which is colorless, and then D should be blue if it forms. But we just get the E color that stays. We said E was weaker than D, so this really means no reaction took place. However, we know then, we probably got a pretty good idea if D is in there, what characteristics happen. If you add D to it, it stays blue, and it stays orange here. And if we have, so we say chemistry-wise from our reactants, here are reactants going to our products, but we didn't have any blue forming, so that means nothing took place. Lastly, you could add, you take a new test tube, and if you add F to it, which is red, if there was a reaction, then F would be converted into something. But we find that it does not get converted, so really no reaction takes place. These two things are mixing together, and you get the colorless D and the F red color that's there. So we say no reaction here, and you get the red color. However, we would know it's in the unknown, which is right here. We would know that in our unknown that it's D, because you get really no reaction in each particular situation. And so you get the three characteristic colors of the things that were added in there of D, E, and F. So your job then for part 3 of your advanced study assignment is to write down a procedure. You'd say, oh, I'm going to add in D into a test tube of the unknown. If the color doesn't change to the blue, or if it changes, or if it stays the blue color, then maybe you just had D minus or NAD. If it did change color, maybe you had something else in there that would indicate something. Maybe another step would be add E to another test tube of the unknown. If the color changes, then what would happen? What would you say is in there if some things took place? Perhaps you could add F, and then you look for color change. This procedure that I'm telling you about is what you would write down, because it tells you what to do and then how to interpret the results. Your example procedure that you're going to write down should do the exact same thing. It should tell us what to do and then how to interpret the results. I'm not giving you all the answers here because it's a nice little logic puzzle for you to think about ahead of time before you get in the lab, because you will do the exact same thing in lab. Especially in the situation or the part of lab where you're dealing with chlorine, bromine, and iodine. Hope that's helpful.